Hello students, my name is Shashank Shekhar and we are doing a crash course on chemistry for the upcoming JEE exam. And today is our 33rd day. So we have started the chapter hydrocarbon and we have completed to up to alkenes. So today we will be covering this part, that is alkynes and aromatic hydrocarbons. So we will be basically talking about the preparation and reactions of both these alkynes and aromatic compounds and see what made this aromatic compound more stable. So let us start with this alkene. So before that, these are the topics that we will be covering today. So this is in detail. You want a look, you can see. So we will start with alkyne, their preparation from different methods. Then the reaction that will be including electrophilic addition and plus nucleophilic addition. Then we will see what is aromaticity and why benzene is aromatic. Then we will see the preparation of benzene. At last, we will do some reactions of the benzene, that is electrophilic aromatic substitution, and some examples we'll see. So let us start today's lecture. So this is the weightage, we have seen it yesterday also. So first start with the alkynes. So what are alkynes? So if first of all look at the structure of the alkyne. So if an alkyne is basically a triple bond, so it is having a triple bond in which the bond length is 1.20 angstrom. Okay, and it has a general formula of CnH2n minus 2. So suppose we have one carbon. So one carbon cannot form this bonds with any other carbon. So we will start with 2. So C2. Then H. N is equals to 2. That means 2 into 1. 2 into 2, 4. 4 minus 2, 2. So it is the formula of ethyne. So this is ethyne. So you can say that the alkynes have a root of ethyne. So it has a suffix called yne. Y-N-E. Now this n is an integral number, so it can be 1, 2, 3, 4, anything. Now moving on to the hybridization part. So this carbon is sp hybridized, in which one s orbital and one p orbital, that is the valence s and valence p orbital, which will be 2s and 2pz. If we are taking the orientation along z direction, then it will be 2s and 2pz. So 2s and 2p will hybridize to form sp hybridized orbital, which is having the shape of a dumbbell like this. And now two hydrogen will come and they will form sigma bond with this carbon, and the carbon will also form a sigma bond with each other. Now the remaining two p orbitals, which are perpendicular to each other, that is px and py, they will side on overlap with the px of another carbon and will form pi bond. We know that pi bond is formed by the side overlap, so this is the case that we are having. So overall it is having a sp hybridization, and this hydrogen that we have, that is attached to this carbon. So if any hydrogen is attached, so suppose this hydrogen, so this hydrogen is acidic in nature. Why is it acidic in nature? Because of the increased S character, because we have seen, so in sp3 we have this 33.33% S character. In sp2 we have this 75 not 25% S character, and in sp we have this 50% S character. Okay, so this is the reason. So this is the reason. So this is wrong. Sorry, this is 25% and this is 33.3%. So as the S character increases, and we know that S orbital is more bent toward the say the carbon or the nucleus. That is why the attracting tendency, or the means electron bonding tendency of this carbon increases, and we know very well that Lewis acid is something which takes electron. Okay. Now it is an sp hybridized carbon, and with the hydrogen it is acidic in nature. Now the thing that is to be noticed here is that it does not form any kind of stereoisomerism. As in the case of alkene, we have this cis trans isomerism. We do not have such an isomerism in this alkyne. And also this alkynes are also called acetylenes because they are the derivatives of acetylene. So this is called an acetylene. And when we add more carbons to it, suppose this is the acetylene that we have here, and we add some group that is R, then it is the general formula of alkyne. So this thing is also called acetylene or derivatives of acetylene. So this can be thought as the introductory part of this alkyne. Now let us move to the preparation. So first we will start from dihalide. So two cases can arise for dihalide, that both of the halogens can be on the same carbon, then they are called gem dihalide, and if they are on the different carbons, then they are called vis dihalide. Now if we put this alcoholic KH upon this, so first we will get this thing. So one of the X is eliminated to elimination reaction, and then if we add another base, that is NaNH2, then the another halogen is also removed. So it happens like this. Suppose a base comes, it takes this hydrogen, this bond comes here, and this X is a leaving group, so it leaves, and we get this alkyne. Now let us see some of the points that should be noted here. The first of all, that the second proton abstraction required a strong base. So this is a strong base as compared to alcoholic KOH. Why? Because this carbon, this halogen, that is a vinyl halide, is stabilized due to resonance. Now second point to look at this here is that this vis, or called vis dihalide thing. So this vis dihalide can give more than one product. Okay, so this can give more than one product, but this alkyne is the major product here. So this JEE-Main dihalide gives only one product, that is alkyne, but this vis dihalide can give two products. Like suppose there is an X here and there is an X here, and suppose it attached to another carbon like this. So first of all, say we remove this carbon. Okay, so remove this carbon, we will get this, or we can say we can have another carbon. So if we remove this carbon, so we will get a double bond here. Again we remove, if we remove this hydrogen with along with this halogen, then we can get a diene system. So this can be also means a product, means thought of product of this JEM dihalide, but vis dihalide, but this alkyne is formed in the major amount. Now next, why is this stable? Why do we require a strong base here? Because it is resonance stabilized. Suppose this is the alkyne that we have, this haloalkene that we have. Now this Cl has lone pair, so it can donate it lone pair like this, and we can have this resonance structure. Again, this can be done like this also. So suppose we have this CH2. Now this double bond migrates here. This double bond migrates here. Okay, and we can get this type of structure also. So due to this resonance stabilization of this vinyl dihalide, it is more stable, and we require a strong base at the second proton abstraction, that is NaNH2. Now the next thing to notice is that trans elimination takes place. So this is a very important point here, that is trans elimination takes place. So if we have, say we have a structure like this, so I am just giving you an idea. So suppose this is the hydrogen that we have, again a hydrogen, again a hydrogen. Then we have to take the staggered conformation of it, and this H should be trans to this X. Then only this proton abstraction can take place. So first of all, this whichever alkene or alkyne we are taking, they orient themselves like this in this fashion, so that the proton that is to be abstracted, suppose this proton is to be abstracted, and this hydrogen is to be left out, halogen is to be left out, they should be trans to each other. Then and then only this reaction will take place, and we will get our required product. So it is a kind of anti-periplanar mechanism. Now moving on to the next preparation, so we can do it using a tetrahalogen also. In that case we use 2 moles of zinc metal, and ZnBr2, 2 moles of ZnBr2 is formed, and one ethyne molecule is formed. So this can be also used. So it is an you can say it is a reduction type of reaction. Okay, so it is preparation from tetrahalogens, because we are having 4 halogens here. So 2 are here and 2 are here. Now preparation of higher alkenes. So higher alkynes can also be formed. So what we will take is take the Grignard reagent. So most of you will say that why Grignard reagent is electrophilic in nature, means nucleophilic in nature. It attacks as a nucleophile on this carbon or any carbon. So why is it so reacting like this? Because I mentioned earlier also that this hydrogen is, say, acidic in nature, and nucleophilicity and nucleophilicity and basicity, 2 are the means competitive factor here. But since this hydrogen is very acidic in nature, this Grignard reagent act as a proton abstractor or as a base, and this abstract a proton from here H. Now we have got another nucleophile. Okay, now this nucleophile attacks on any halogen, haloalkane, and we get our required product. So suppose this is the thing that we are having here. So if we react it with CH3I, then this CH will attack this CH3 and we will get it as CH triple bond C CH3 plus MgI2. So we can form this higher alkyne using this. So first we will convert this alkyne to say this a nucleophile by reacting it with the Grignard reagent. Then we will react this with any haloalkane and it will give a nucleophilic reaction. Now we have another method, that is decarboxylation, sorry, Kolbe electrolysis, which uses decarboxylation to give our alkyne. So what happened is that this is a sodium malate. Okay, why? Because it's a malic acid and we have salt of this sodium, so it is sodium malate. Now this sodium malate can exist in two forms. Sorry, this is wrong. So it will be like this. So since it is a salt, it can exist in ionic form, that is negative, that is cation, sorry, anion and cationic form. Now if we do the electrolysis of it, so at the anode we know that the reduction will take place and it will take 2 electrons. Okay, so it will take 2 electrons and it will form this kind of thing. Now the decarboxylation will take place and we will get this alkene. So you know decarboxylation, so it happen like this. Suppose this is the thing. Okay, now this leaves and we have this. So if you consider this reactant here, so if we write in more expanded form, it will look like this. Now this will come here, this will go there and it will leave. So we will get a alkyne here. And at the cathode, what will happen? This 2Na will take 2 electrons and we have 2Na, and 2Na plus 2 electron can also form NaOH and H2. So through Kolbe electrolysis, alkyne can also be formed. So it can give alkene also, it can give alkyne also. Now let us see some preparation of ethyne. So ethyne can be prepared in various ways. The first one is from metal carbide. So we use this calcium carbide here. In the presence of water, it gives our alkyne plus calcium hydroxide. Second, so this is a manufacturing method which it is used in industry. So we take simply this methane and pass it through electric arc, then we will get this thing here, that is ethyne. So this is ethyne, sorry. Next is Berthelot's method. So in this we take this 2C and we react with H2 in presence of electric arc again, so we get this ethyne. Now this is a haloform reaction, so it is a very important one. So we take this haloform here. So this is not a haloform reaction, but this is a reaction which is done using haloform. Haloform reaction is a different thing. So we will take this CHCl3 in presence of say silver, it gives us this alkyne. Then also the partial oxidation, means we are doing the partial oxidation of this 4CH4, then we get this alkyne. So you should remember this method because it is asked directly in 1 marks also, in 4 marks also. Now let us move to some reactions of this alkyne. So first we will be looking at electrophilic reactions. So let me make one point clear here, that alkyne can act both as a nucleophile and electrophile. So it can give electrophilic addition also and nucleophilic addition also. So first we will look at the electrophilic addition. So in electrophilic addition, first we will see the addition of this hydrogen. So there are two possibilities of adding hydrogen to this alkyne. The first is the catalytic hydrogenation, in which we use this metal, that is PDPT, and it is called Lindlar catalyst. And second is the case that we can take sorry, this is the Lindlar, this is not the this is written wrong here. Okay, so this is the Lindlar catalyst. Lindlar catalyst. So this is just in the presence of an sodium metal, so it gives electron and forms. So if you take this H2 in presence of PTPD, so it will give us cis alkene. Okay, and if we take this Na here, or the NaNH3 in the presence of sodium metal, it gives us trans alkene. So in this case we are doing a partial reduction, and if we do the full reduction here, so if we do this full reduction here, then we will get this alkane also. So first of all, look at the mechanism. So this thing, that is hydrogen, is first absorbed on the surface material, Now in the second process, this alkene is also made absorb on this surface metal. Now activated complex is formed, ACT, and which gives us the final product, that is alkene. Now since this both of this hydrogen will add upon like this, so it will go like this and it will go like this, and there we will have a cis faction of addition. But in case of this electron means, if we use this sodium metal in presence of NH3, then this sodium metal will give one electron and we will form a trans type of intermediate, that is radical anion, and this negative ion will be on the opposite side of the radical. Now this negative will take H from this NH3 and will form this kind of thing, that is having a radical on the trans of this hydrogen. Now again this sodium metal will give one another electron, and we will get this anion again, and which will take this H from this basic NH3 ammonia, and we will get a trans alkene. So addition of hydrogen can take place in two ways. So if we use any metal for this reaction, we will get a cis alkene, and if we are using say sodium in presence of NH3, then we will get a trans alkene. Now let us move to the next thing, that is hydrogenation and hydroboration. So in the first case we are adding HX, and in the second case we are adding BH3 or B2H6. So we have used this hydroboration in this alkene also, and you will use in alkyne also. So let us see the difference between the both of this. So first, what is hydrohalogenation? So this hydrohalogenation mainly takes place through this carbocation formation, and X is added on more substituted side. So this should be kept in mind always, that this halogen is added on the more substituted side. So if you are adding one equivalent, we will get a mono alkene, okay, or you can say haloalkene. And if you are taking two equivalent of HCl, then you will get a dialkene, sorry, dihalogen. That is, in this case, if you are using hex 3 ion, we will get a 3,3-dichlorohexane. Now what is the mechanism that we are having here? So first upon this, H is added on this side, and we will get a positive carbocation. So the carbocation will form on that side in which is more stable. So if we are having a 3 degree, it will be forming 3 degree first, then 2nd degree, and then 1st degree. And we will get a geminal dihalide. So this should be kept in mind that we will get a geminal dihalide. Now if we add this B2H6, it will also be added in the same way like this. So BH3 will be going there, okay. Now it is not going in this direction, it is going in the opposite direction. Why? Because it is a kind of concentrated, it is following a concentrated mechanism, and in concentrated mechanism the steric factor is acted more upon. So since we are having a steric hindrance on this side, so BH2 goes on this opposite carbon, that is this one. Now we get this type of intermediate, okay. So this is the intermediate, sorry, you cannot call it, we can call it intermediate because it's very stable. This BH2 will again act with one more mole of this alkyne, and again act with one more mole of alkyne to give 3 alkyne that is added to it, and then we will do its hydrolysis in presence of H2O2 and OH minus. So we will get this thing. So BH2 will be removed and OH will be placed here. Now since we know that enol form is less stable than keto form, then we'll get a aldehyde and this ketone accordingly. So suppose if it is a terminal alkyne, we will get an aldehyde, and if it is not a terminal alkyne, means this carbon is in the middle, another carbon is added to it, then we'll get a ketone. So these are the products of this hydroboration and hydrohalogenation of this alkyne reaction. Now next, let's move to the nucleophilic addition. So what is the nucleophilic addition? It happens, the alkyne donates its electron. So in the electrophilic, we are getting electrons from the another thing. Now in nucleophilic addition, this alkyne will donate its electron. So the first one is the oxymercuration or demercuration. So if you want to look at the mechanism, it happens like this. So we have this HgSO4. Okay, so we have this HgSO4. Now what happens is that this Hg is 2 plus oxidized. This alkyne gives its electron density to this Hg2 plus metal, because electron is negative in nature, it has a negative charge, and this Hg2 plus or mercury ion has a positive charge. So it forms this type of activated complex, okay. And now we have formed an activated complex, and since we are taking this H plus and H2O. So H2O is added in this fashion, so OH gets here, and H plus goes on the opposite side. So it happens in this which is less steric. So if this is less steric, OH will be here, and if this is less steric, OH will be here. Then further we get the reactant. Now since this again this enol form is less stable, so we'll get this ketol form. So this is the ethyne reaction in of the oximetric reaction of this ethyne. Now let us move to this ozone-lysis. So if you look at the ozone-lysis, if it is not clear, let me do it for you for here. Suppose we have this ethyne here, okay. So we have this ethyne here. Now we have this O, 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 okay. Now we have this O minus here. Now since we know that this is acting as a nucleophile, so it will be added like this. Now upon further say means depending upon the reagent that is added further, but it is reducing or reducing reagent or oxidizing reagent, we will get the aldehyde and alcohols respectively. Now we will take the case of halogenation. So in case of when we are taking HX, so when we are taking this HX thing and we are adding two equivalent, then we are getting a gem means both of the halogen are added on the same carbon. But in case of this, we are taking Br2 and this kind of substrate is formed. You can say intermediate is formed. The electron density is donated to this Br and this Br leaves. Now this Br minus attacks on the up trans side and we get this trans dihalide, and it is cis in nature because both of the halogen are on different carbon. Now further this alkene also goes this nucleophilic addition, and again this Br is added and we get this type of tetrahalide. So this was all about the alkyne reaction. Now let us move to this thing aromaticity. So what is aromaticity? So we have some aromatic compounds here. So let us see what makes this compounds aromatic. So there are certain rules that should be followed. The first one is that planarity. So this if something has to be aromatic, it should be planar. And what is which carbon is planar? We know very well that this sp2 and sp carbon. Only these two hybridized carbon are planar, and sp3 is not planar because it is tetrahedral in shape. So for a thing to be aromatic, it can be sp2 or sp. Now this sp factor will be means outdated further when we will have this another factor that is of conjugation. So since alkyne is not having this conjugation type of thing, so this sp2 carbon is only preferred for aromatic compounds. So we have this conjugation, so we should have the conjugation here. And the fourth is that it should have 4n plus 2 pi electrons. So let me make all this point clear by using these examples. So if we take the example of cyclopentadiol here, so first one is planarity. So it should be planar. We know that every carbon should be sp2 hybridized. So this is sp2 hybridized, this is sp2 hybridized, this is sp2 hybridized, this is sp2 hybridized, and plus this is also sp2 hybridized. Now the next thing is it should have a conjugation. So it is having conjugation very well. Why? Because suppose this is the lone pair that we have here and negative charge due to this lone pair. So it will move here and this will move here. You will get a resonance structure like this. So this negative charge can move all along this ring. And at last we will get the same structure. So if you keep on rotating this thing, it will resonate through whole of this ring. Okay, so it is completely in conjugation. So the second criteria is to be conjugated, and the fourth criteria is that it should have 4n plus 2 pi electrons. So what is the meaning of this? So if we take number of pi electrons here, so it is 2 plus so one pi bond will have 2 electrons, so 3 pi bonds will have 6 electrons. So 4n plus 2 pi is equals to 6 pi electron. So if you calculate this, you will get n is equals to 1. and it should written here that L can be 0, 1, 2, 3 or any another integral. So it cannot be negative, so it is not possible. Also it cannot be negative, or plus it cannot be fraction, so it should not have a fraction thing in it. So if we take n is equals to 1, we will get the benzene. So similarly it has also, so this is also a pi electron, so do not get confused. So it is also a pi electron, so this is a pi electron plus 2 plus 2, so it is total of 6. So n is equals to 1 here also. It is also 6 pi electron, so it is n is equals to 1. So all of these have 6 pi electrons and n is equals to 1 for each of this. Now considering this one, so all of the carbon are sp2 hybridized first of all, so it is planar. So if you move the conjugation is also conjugated. Now the third one, it should have n pi 4n plus 2 pi electrons. So how many double bonds are there? So 1, 2, 3, 4, 5. So 5 double bond means 10 pi electrons. That is n is equals to 2. So it is also a valid number. Now similarly, we have this polycentric compound also, which has the anthracene and the phenanthracene. So it has 14 pi electrons, where n is equals to 3, and it is planar in nature. So this is the very basic definition of aromaticity, and it is followed for all the compounds. So later on these things can become complicated, but for now it is good enough. Okay, so these are the things. So we have this examples also. You should remember the examples. Suppose directly if the examples come, you can conclude an answer without doing any work. Or if not, you must remember this rule, all of these 3 rules for aromaticity. Now let us have a proper look on this benzene. Now if you look at the structure of benzene, they can exist in 2 forms, that is this one and this one. So we can have, so in this, if we name this all this carbon, so it has 1 2 double bond, 3 4 double bond. So this is 1 2 double bond, 3 4 double bond, and 5 6 double bond. And the second possibility is that, so we can have 1 6 double bond, 2 3 double bond, and 4 5 double bond. So these are the 3 possibilities for this structure and 3 possibilities for this structure. So you can see very clearly that 2 structures are possible for the same compound, which are like this. But later on some experimentation shows that this neither exists, as this is not a double bond, nor this is a double bond. They all are partially double bond. Means not there, so you can say it is a kind of 1.5 contribution to all of this. So it is 1.5. So bond order is 1.5 for each of this. Not 1, not 2, it is in the middle. That is 1.5. Because when we calculated the bond length, it was seen that its bond length was not of the single bond nor of the double bond. It was in the middle of the both of this. So the bond order was considered to be 1.5, that is in the middle. And this pi electron was distributed over all this carbon. So it is now this all this carbon are shielded by this pi electron cloud. So this is the pi electron cloud, and this is the pi electron cloud at the down, and all of this carbon is in the middle. So it is forming a sandwich kind of structure here. And the final structure which was concluded, it looks like this, or you can say in a condensed form, it looks like this. So this is all about benzene. So if you look at it, so it is aromatic in nature. We have explained why. Now let us look into some of the preparation of this benzene. So first is from the ethyne. So we are taking a ethyne and passing it to the red hot iron tube at very high temperature. And what we are getting is a benzene. So it is basically a concentrated mechanism. So it goes like this. So suppose this is the thing that we have here. Then we will get this bond formation like this. So same thing is written here. So it is a concentrated mechanism. It happens in one step. Okay, so sorry for this. It is written twice. Now the next we are taking a phenol and doing a reduction of it in the presence of zinc. We are providing heat and we also get a benzene. So basically we are converting phenol to benzene. So there are many more methods like this. So we can prepare benzene. So we can take any derivative of the carb of this benzene and we can further reduce or oxidize this to get our final product, which is a benzene. Now let us move to the most important part of this benzene, that is the electrophilic aromatic substitution. Now before moving to this electrophilic aromatic substitution, let me make one thing clear here, that this benzene cannot go, never means it can go this nucleophilic substitution reaction, but under drastic condition. So we can write it here that nucleophilic substitution is not general. I'm using the word general here. So at drastic condition it can undergo, but I don't think that it is useful for you that you consider any nucleophilic substitution of this benzene. So what are the reasons behind it? So if you look at the structure of this benzene, you must have seen the electron clouds that are present here. Okay, so these are the electron clouds that are present here. So for a nucleophile to come, it should have some space, or you can say so it's a negative charge is coming. Okay, so a negative charge is coming. Now due to this cloud that is present here, it is repelling the negative charge to come on this benzene. Now due to this reason, it does not allow this nucleophilic addition reaction. Okay, so the first and the foremost reason is this. And the second thing, so if something goes a nucleophilic addition reaction, this aromaticity of this benzene is removed. This is the second reason. The first one is this electron cloud. The second one is that removal of this aromaticity. Now, due to these two major reasons, the benzene does not undergo nucleophilic addition reaction. So it undergoes this electrophilic substitution reaction, electrophilic aromatic substitution reaction. So what happens is this: we take an electrophile like this. Now it has a pi electron. This pi clouds attack on this electrophile, and we get this intermediate, which is a carbocation, which is having a positive charge here. Okay. Now what happens is this: we take a base like this. Okay, so we take a base like this, and we abstract this proton from here, and we get this substituted benzene. Now one thing is to notice that here is that this compound that we are getting here is very stable due to the resonance stabilization. Okay, so this is forming a resonance stabilization. How? Okay, so how it will form? So let me draw a diagram for you. So if this electron will go here, okay, so it will go this side. Okay, or you can say this is going here. This one is going here. So we'll get another structure that will look like this. Okay, now again this electron will move here, and we get back the same structure that we have here earlier. Now one point I want to make here is that if something is forming two resonance structure by movement of electron, and if three resonance structure or four resonance structure, and if two of those are same or equal in nature, means they have the same charge position, same everything, then that compound or that structure become very stable. So if you have two resemblance of the same resonance structure of the same compound, then we can say that this thing is very stable. So you can see very clearly that after the movement of this electron, we got this thing back. Okay. Now due to this reason, it is very stable. And if we draw the resonance structure of this, it will look like this. We have a positive charge here. We have this hydrogen. We have this electrophile. So this pi electrons are located all over this benzene. Now further, this where is the base which take this hydrogen, and we get our substituted benzene. So this is the basic reaction of electrophilic aromatic substitution. Now for the electrophilic aromatic substitution, this electrophile should be very strong. So if it is strong and very strong enough, then and then only the electrophilic aromatic substitution will take place. So let us take some examples of strong this electrophilic substitution. So first one is the Friedel-Crafts alkylation. So we take this Friedel-Crafts alkylation.